session started a little bit more complicated. We were going to build Skynet originally. Not really. We were actually going to build a data classifier to identify mushrooms and whether they're poisonous or edible. Then we were going to build a convolutional neural network to identify cats and dogs. Then I started talking to some of the other session speakers, and we realized that a lot of the sessions are very high level. We kind of want to be able to, or at least I wanted to make sure that everybody walks out of here with some kind of a understanding of every concept that's spoken about. So I went a little higher level, a little simpler on neural networks. We're going to do a little bit of history on what neural networks are. We're going to do a little bit of theory, very high level, very simple. So if you have no idea what machine learning is or neural networks, you'll figure it out. People who are already a data scientist probably going to be bored out of your mind, so have fun with that. And then finally, we're going to move to kind of a live code demo. So it's going to be almost like a tutorial, except not a tutorial because I don't want you to be bored. We're going to go through, build a neural network that's going to look at data that's from a biopsy from a potentially tumorous cell. We're going to look at that data, how the cells were tested, and then classify whether the patient does or does not have breast cancer based off of that data. So it should be pretty cool. So before I start, a lot of times, let me introduce myself first. Sorry. I'm Brandon Boynton. I'm the CEO at Vemity AI. We build a platform that does exactly what we're going to do, except without any code or theory. I came here to speak just to talk about neural networks, but a lot of times people ask me, hey, what is AI? How do I get into that? Should I get into it? And the very first thing I always say, and it's very important, is if you're thinking about getting into data science, into neural networks, machine learning, I'm sorry, I'm probably blocking the link. But if you're thinking about getting into that field, it's very rewarding, very exciting. It's cutting-edge technology. It's a lot of fun. Your friends think you're cool when you tell them you can build an AI in 15 minutes, so that's neat. But there's one very large pitfall. And that's primarily because you're always looking over your shoulder, you're always watching your back. It's a very dangerous field because you never know when somebody's going to come back from the future. Some lady is going to try and kill you to prevent the robot apocalypse. All of you data scientists know exactly what I'm talking about. Anyway, a little history about AI. I think it's a good thing to start with some history so that way you get an idea where we came from, where we're at now. In the 1940s, scientists were kind of guessing to figure out how does the brain work. They didn't really have a clue at all how neurons worked, how we remembered things. And eventually they realized that learning is facilitated by fired neurons strengthening their connections, creating patterns of stronger neuron chains representing specific memories or learned behaviors. This theory was eventually converted into a mathematical model called the perceptron. And while it was a great theory mathematically, it was really awesome, theoretically it was really awesome, computers could not handle it. This simple model that you see down here was ridiculously tough. Eventually, the mathematical models were analyzed and led to the use of the perceptron, which is this value, or this graph down here. A perceptron consists of at least a minimum of 3 nodes, so what you see here are at least 2 inputs and 1 center node that leads to an output. There we go. Sorry, I'm a little off. I got 2 inputs, a center node that leads to an output in its simplest form. This very simple graph was finally built by Cornell and the US Navy, and it looked like this on the left, which was the Mark I perceptron. This massive computer accomplished this very simple task. It did basically nothing. It was millions of dollars of funding that did really nothing. From there, Stanford led the charge with what you see on the right, which was nicknamed the Mark II perceptron. Millions and millions of dollars of research were pumped into this to produce this massive machine that was built to model the perceptron. It would listen to a conversation on a phone line. It would analyze the bits, zeros and ones going through, that would go into the inputs. It would use that to predict the next bit. 1/16,000th of a second. It really did nothing. It predicted the next bit, which was cool. Theoretically, it was awesome. It was predicting the future. But 1 bit is nothing. Stanford looked at it. They were like, where did our millions of dollars go? Like, what is this? And because of that, one of the professors that was heavily involved with the program published a paper that basically explained computers will never have the computational ability to focus on what he was calling a biological processing model, to be able to process things like the brain does. So because of that, not necessarily because of that, but in part from that, traditional von Neumann architecture took over. Funding for research and AI development dwindled. Really, nobody cared about it. And also, at that point in time, the general public started to fear the idea of an artificial machine thinking like a human. They were so scared that these machines are going to take over. So because of that, the second most notable, where is it? I'm a little off. The second most notable AI winner began. So an AI winner, if you're not super familiar in both the AI world and the business world, it basically means nobody cares about AI. Nobody's offering funding or research for it. So from there, from the 70s to the late 2000s, there we go, now I'm back on. From the 70s to the late 2000s, AI winners came and went. I'm skipping over a whole lot because a lot of it doesn't really matter, but a few major and notable advancements were made, such as the discovery of backpropagation, as well as better training and distributed processing. So those kind of would pull us out of an AI winner, be cool, some universities would pump some money into research, and then they'd give up and be like, yeah, this is going nowhere. Terminator, the Terminator series, which is a general theme here, kind of started one of the AI winners. People got scared of AI, which is pretty funny. So even still today, at that point, a lot of simpler machine learning techniques kind of took over, like the support vector machine, k-nearest neighbor algorithms. They took over. A lot of people consider that to be AI, if you'd even consider a neural network to be AI. And even still today, a lot of products that claim to be using artificial intelligence are really just using very, very simple regression algorithms or k-nearest neighbors or support vector machines and claiming that that's artificial intelligence. So more recently, we've kind of been an AI winner for a very long time until more recently, around 2010, there was the ImageNet competition that started to bring us out. And then in 2011, Geoffrey Hinton published a paper describing that training and inferencing neural networks can be greatly accelerated using a GPU, which really brought us out of this old, clunky, slow mindset of training into the modern day where we can train. What you're going to do right now, this is just on your CPU, but what you're going to do right now, it trains it almost instantaneously. The technology has progressed incredibly. If you're doing a bigger data set and use it on a GPU, you could do a much larger data set, much better, more accurate neural network model very quickly. So from that, it's a little bit of history, kind of caught you up in maybe like 5-10 minutes. From there, what exactly is a neural network? Again, a lot of you are going to be really bored with this, but it's really important everybody has a deep understanding of what this is, or a shallow understanding of what this is before we start to go through the code. So there's a large number of different neural network architectures and configurations, but it all started with this down here on the bottom. This was the simplest form of a neural network or machine learning, deep learning, which is a perceptron. Basically, again, you have the inputs. It goes into one function in the center. It's going to act as similar to a bias. It's going to go through an activation function and then give you the value. From there, people started to realize, let's put them together. The accuracy is OK with this. We'll put it all together and form a multi-layer perceptron, which turned into the shallow neural network. So what you see on the top is 4 inputs followed by a hidden layer. Every node is connected to every node in the next layer, which is called a dense or fully connected layer. And then every node in the hidden layer is connected to the output layer. Now, we'll get into training in a minute, but basically this would provide pretty accurate results. It took a long time to train, and as GPU technology has gotten better, computational technology has gotten better, we've been able to advance into deep neural networks, which has multiple hidden layers and is typically we can handle a lot more parameters going in. So looking a little closer here, each circle represents a neuron, what we're going to call a neuron or a node, in a fully connected layer, which is the most basic kind. Each neuron has a bias in the simplest form, and then each connection between a neuron and the next neuron, that's a connection. Each connection has a weight. So the mathematical model is to move through, take the data in the beginning. You're going to slightly adjust the data until you get to the end, going through each bias and each weight, slightly adjusting the data until you get to the end, you get the result. And that's either prediction or when you're training. This is where training comes in. So a neural network by itself is basically pointless. This thing right here means nothing, because you send data through it, it's going to give you gibberish. Nobody cares about it. Until you train it, it doesn't do anything. When you train it, we're basically going to give it a whole bunch of inputs. We're going to give it one input at a time, get the output, see what it is. Probably going to be 50-50 for a binary classifier. We'll say, it probably shouldn't have been that, or it shouldn't have been that. The actual answer for this set of input was 1. So depending on how far we are off, that's our cost function, we're going to backpropagate back through, train, adjust the weights and biases equal to how far we were off in order to get a better answer, depending on our learning rate we've established. And through time, through many iterations of training, we'll slowly find a model that fits exactly what we're trying to classify. So without going super into the theory of the mathematics and the graph theory, that's essentially what training is. So after we train, well, when we want to use it, we'll inference is the key word there. We'll give it a new input that's formatted just like the training data, then it'll give us a predicted output that matches what it was trained on. So there's a number of vocab words to learn, but a lot of the rest I'll kind of explain as we go through the code demo. Again, if you're not done with setting up the environment, the link's not there anymore. If you're not done setting up the environment, talk to that guy. What we're going to do from here, which I think is important, because again, I want everybody to walk out of here feeling like they learned something, not like everything was just straight over their head. We're going to build a classifier, like I mentioned earlier, that's going to identify whether patients do or do not have breast cancer based off of test results. And what's really interesting about this is a very popular data set. You can find it online pretty much anywhere. What's really interesting about this is you can easily create a neural network that will predict whether they do or do not have breast cancer much better than most any physician. Because a physician would look at this and see, like, you look at the fifth row down, they'd look at the numbers and be like, oh, those look like bad numbers, I don't know, could be cancer. Yeah, I'll go ahead and diagnose you, we'll see, that kind of thing. An AI is going to be able to look into 9 separate dimensions and be able to classify based on the numbers in a very mathematical and factual sense, rather than using reason, which kind of inhibits and prevents the physicians to be able to diagnose as accurately as this. Obviously, there's a lot of other factors that go into it. This is a pretty interesting data set because of that. So what we're going to do is create a very simple deep neural network. Actually, I think we're going to do shallow. We're going to build a neural network that's going to have the inputs going in just like this. Each value you saw here, this number, is going to be inputted into these nodes. That's going to be sent through until it's going to give us a value at the end, whether the test results show that it was benign or malignant. Then we're going to compare that to what we think it should be, get the accuracy, and it should be pretty fun. So let's go ahead and start with the demo. Again, the source code is on the repo, so if you get lost, if you did something wrong, or you can't see what I'm doing, you can copy-paste that. There's that dude, too. So you can do this however you want. I'm going to go ahead and create a new folder. Let's name it BC. Oops, that's not BC. Name it BC and put it on my desktop so it's easy. I'm going to drag the data set in because we need that in there. I have my terminal right here already in desktop/BC. So we have, there we go. So we have the data set in there. I'm going to open that up, and Adam, feel free to use whatever text editor you want. Find desktop, BC, open it up. We're going to create a new file. I'm just going to name it bc.py. So this is a single file that's going to handle everything. There's 4 major steps in using a data classifier. The first one is preprocessing. That's going to be the most intensive for us because we got to format the data in a way. That's a good point. Let me add my font size real quick. Does anybody see that on here? I'm probably like looking over it because I'm all nervous and stuff. There you go. Okay. Let's do like 40. Yeah. Can everybody see that fine? Is that appropriate? Cool. Okay. So there's going to be 4 major steps. One, we're going to pre-process. That's going to be the most intensive for us. Then we're going to move to designing the neural network to make it fit the data. Then we're going to train the neural network, and then we're going to inference on it. So it should be pretty simple. I only have like 3 pages of very largely printed notes, so it should be quick. First, we're going to import all the libraries that you just recently added to your environment. So we're going to import first pandas. That's not how you spell pandas. Pandas as PD. Pandas is what we're going to use to turn our data set into something, to turn our data set into something that we can easily manipulate. We're going to import Keras. Keras is our high-level wrapper for TensorFlow, so you don't have to do the matrix calculations yourself. Now we're going to import NumPy as NP. Then from keras.models, we're going to import sequential. And if you don't want to follow along, you can just look at the source code and copy-paste this. Import sequential from keras.layers. We're going to use 2 layers. Import dense, which is our fully connected layer, and activation. And then lastly, from sklearn, because sklearn has a lot of really good metrics, we're going to use one of their simplest metrics, import accuracy score, so that way we don't have to write the function ourselves. It's lagging a little bit. From there, so we got everything imported. We're going to enter our config variables. So this is all of the stuff that pertains to how the neural network is trained. We're just going to put it all up here so you can edit it, move around, see what you like, what you don't like, what provides a better accuracy, what doesn't. So first of all, we're going to do test split. Test split is what percentage of our data are we going to reserve for determining accuracy. I put 10% in. That means 90% of our data. There's 700 rows in that data set. It's pathetically tiny. There's 700 rows, so we're going to use 630 rows for training it. And then from there, I see a lot of people squinting. If you want me to make it bigger, somebody just shout that out. So we're going to have 630 rows reserved for training, and then 70 rows are going to be reserved for testing. So after it's trained, we're going to run 70 values through it, see if it gets it right. If it doesn't, get the average of that and see what our accuracy is. Whole symbol is going to be equal to a question mark. As a string, it lagged again. If we look at our data set, let me pull it up right here. If we look at our data set, there's some holes in it. So right here, there's a question mark. So that means for whatever reason, for this value, which is bare nuclei on that patient, they didn't get a value. It's very normal. We got to account for that. We have to fill in some kind of integer. What we're going to do is get the average of every value in the column. For a small data set, it's pretty easy to do. We're going to get the average of every value, put that in there so it has as little effect on training as possible, so that hole doesn't really do anything. So we're going to denote, we're going to specify that the holes are denoted by a question mark. From there, our prediction column, the column we want to know, again, going back to our data set, that's class right here. 2 is going to mean benign, 4 is malignant. So we want to guess the class or predict the class, so we're going to create prediction column as a string. Class. How many epochs? Again, if you're familiar with this is probably really boring, but everybody needs to know. An epoch is every time you run through the whole data set, that's one epoch. You run through the whole data set, you might get 50-50 accuracy. You run through it again, that's a second epoch, you might get 80% accuracy. You run through it another time, you might get 90%. Every epoch is just running through the whole data set. So we're going to do 10 epochs of training. Then learning rate. Learning rate determines how much impact does every single example have on the values. So when you're backpropagating, when you're training through the neural network, how much impact does each answer change the neural network? So we're going to make that really low, 0.001. How many inputs is 9, because we have 9 things to take in as an input. Very simple. And then how many outputs is 2, because there's 2 options. So that's it for config variables. From here, we're just going to preprocess. So again, this is the most complicated part for us because we're not doing really anything crazy with neural networks. So preprocessing is actually kind of a lot in this case. So we're going to create a new variable, df, data frame, equals pd, which is our pandas library, read CSV. Put it in CSV format, so it'd be really easy to pull in. And make sure that your data set is in the same directory. We're going to pull in breast cancer Wisconsin, which is the name.csv. From there, if you look at our data set, we have an ID column right here. The ID has absolutely nothing to do with whether they do or do not have cancer. So we want to drop it. If it did, that'd kind of suck if you're the unlucky one to get a bad ID. So we're going to drop that. We're going to have df.drop, columns ID, axis equals 1, because we're doing a column instead of a row, and in place equals true, so we don't have to create a new variable, save on memory. And then from there, we get to the important step where we're replacing any hole. So this takes a little bit of logic. It's going to be super simple, but maybe difficult to follow along. So first, we're going to create a list of all the columns, df.columns.values, and then we're going to loop through them. So for call and calls, create a new empty array, only nums. Also, I want to say, some of you guys are going to cringe. Some of this code's very unorganized. I did it in a way, so rather than doing a bunch of stuff in one line, I wanted to go line by line so everybody can kind of see what's going on line by line. So you're going to look at this. I have a while true loop later on. You're going to cringe and probably want to cry. But it's just to make it as simple and quick as possible. I just wasted that time we're speeding up by explaining. So then for row, once we're in the column, we're going to go row by row. So for row in df call, let's lag it again, dot to list. We're going to loop through that. Have if the variable is a number, then we don't want to replace it. So if instance of row is equal to an int long float or complex number, then we want to add only nums dot append row. So we're going to add that number to our list of only numbers, basically leaving out everything but leaving out the question marks. Then call mean is going to equal np. We're going to use NumPy array so we can do some fun stuff. np mean only nums. Dang it. That's what happens when it lags. So it's still pretty simple. We're going to create a new column equals the old column, so df call dot toList. And then we're going to loop through for row and new column. And I know there's better ways to do this, so don't stand up and yell at me. For each row, we're going to look if row equals whole symbol, then new column row equals call mean. And if I write a typo or something that I don't catch it, please yell at me so we don't have to deal with debugging later. And then df, we're going to replace the old column with the new column. df equals new call. So this is the hardest part of the preprocessing. Then from there, we need to set up our data frame so the neural network can understand. So we have everything converted to integers, because everything converted to numbers. Everything going in has to be a number. So then we're going to convert that into something the neural network can understand as far as its formatting. So first we're going to split up the rows. So how many test rows equals an integer of the length of df dot, my computer's huffing and puffing up here too. df.index, we're going to get the length of that, multiply it by the float value of test split, and that's going to give us how many to test with. So it's going to be 10% of the rows, not rounded to the nearest row. And then how many train rows is going to equal length df.index minus how many test rows. Pretty simple. And then train is going to equal df.head. So train is going to be our array of all the values. So train equals df.head. How many train rows? And then test is going to be the exact opposite. Test equals df.tail. How many test rows? So we're splitting it up. From there, we need to format it still even more. The typical convention with training neural networks is you're going to pass the input in as capital X. The output's going to be lowercase y. I don't know why. It's what people do. So x is equal to np.array train.drop. We're going to drop the column that we don't care about, which is prediction column. It's going to be 1, which basically means we're just going to pass it in as its own variable. And then as type, we need to convert it to a float. So everything can be a float. Oops, that's lowercase. And then we're going to do one more thing to x. X equals np.array. Again, making an array. It should be already, but just in case, I guess. np.array.reshape, because it's a multi-dimensional array, so we got to make sure it's in the shape that the neural network can understand. So how many train rows? It's going to be first dimension. Second dimension is how many inputs. So it's going to be a multi-dimensional array with the number of objects in the first array is how many train rows, and then the second array inside it is going to be 9, which is how many inputs. Then finally, y is going to be our output. We're setting up np.array df, and we only want the prediction column because it's the only thing we care about. Oops. Cool. Okay, and then from there, the last thing we have to do is convert our values for outputs into one-hot encoded variables. So if you saw on that chart, I'm going to pull it back real quick. I do. Thanks. Ah, thanks. I knew I'd do that at some point. So if we look at this chart right here, now what we're doing is actually a categorical classifier instead of a binary classifier. We have two outputs right here on benign and malignant. So that's either going to give us benign or malignant. We're going to convert our answers from 2 to 4 to one-hot encoded arrays. So it's going to give us something like this, This basically means that the right side is higher. That means it's giving us the second value. Otherwise, it'd be flipped the other way around. The actual answer should be something like this, which means this would be malignant because the first value is 0, the second value is 1. It's a one-hot encoded array. So we need to convert our y's into that to train with. The lag is killing me. So from there, label vals, I'm just going to hard code it, equals 2 and 4, because those are the two possible options. New y equals empty array. For label in y, loop through every label, empty tensor equals 0, 0. So we're going to change that into 0, 1. Modified, gosh, I think it's because I have it plugged into the screen. Modified tensor equals np.array of empty tensor. So we can do some funky stuff on it. Label index, we're going to get the index of the label in y equals label vals dot index label. And then lastly, we want to make our modified tensor. There you go, modified, nope. And make our modified tensor equal to label index equals 1. So let me explain that because I kind of got a little off. One last line. New y dot append modified tensor. So what we're going to do here, it should be pretty simple. Now we have the empty tensor and the label vals. So what we're going to do is find the index of y, that particular y in here. If it's 0, we're going to convert index 0 and empty tensor into 1. If it's 4, we're going to turn this one into 1. So we're going to get one hot encoded arrays, which are going to look like, gosh, they're going to look like this and the opposite. So this would mean cancer. This means not cancer. And then from there, so we're going to create y equals new y. We're going to override y. So that's now our converted outputs into one-hot encoded tensors. So now we need to do the same thing with x, except we've already done it with full y, so we got to split y up. So test x is what we're going to do to get the accuracy. np.array, test, do the same thing we did earlier. Test.drop, prediction column, comma 1. Lag. Dot as type, it's a float. So you can all be floats. And then same thing we did earlier. Test x, capital X, equals np.array. Test x. Dot reshape. And we're going to reshape it for same as last time, but how many test rows, and then again, how many inputs. So we're getting really close. And then lastly, our test y, we already converted all of y, so you didn't want to have to do that twice. So test y is just going to equal y, and we're going to get how many train rows. So we're going to divide that up to just the ones that we want for training. And then y equals y, actually got to make y equal to what's not in test y. So y equals y, everything before, how many train rows. Cool. And then last thing, we're going to convert y into np array so we can do funky stuff on it. It's pretty much all you do with np arrays, is funky stuff. And then y true, which is what we're going to test against, equals test y, is to rename it to fit conventions. And finally, y true equals np.argmax of x, because we want the highest value to be the correct one for x and y true. Sweet, okay, and then from here, we're moving on to creating the neural network architecture, so it gets a lot less mundane and boring and more interesting with neural networks from here. So we're going to create the architecture. We're going to create a new variable named net, not new, net equals sequential. And that is our Keras model for neural networks. From here, it's kind of important. With Keras, there's a little bit of a problem if you're training over and over and over, which you're probably going to do because it's a tiny data set. You need to clear the last TensorFlow graph, otherwise it'll interfere with it for some reason. So we're going to import TensorFlow. Let's do TensorFlow.reset default graph. You can just copy paste this from the source code. And then from TensorFlow.python.framework import ops. Another option if you're using Keras is you can use Theano for it instead of TensorFlow. I tend to like TensorFlow a little bit more. I feel like it's more supported. So I'm going to reset the default graph again. Now finally, create a new object session. We're going to start a new TensorFlow interactive session. And there we go. So we're done with TensorFlow. Now we can go back to Keras, the fun one. So we're going to add a layer to net. So net.add. We're going to add one dense layer, which is a fully connected layer, as you saw on the graph. This is going to be, we already have the input layer that's interpreted by Keras. Then we have one layer that's going to match what the input layer was, just to make it simple. So we're going to make that dense. It's going to have the same number as nodes as how many inputs. It's going to have 9. Then we also have to specify the input dimension, which is what the input layer is going to be. So input dimension is also going to be how many inputs. Also, these values I put here don't matter. You can do whatever values you want. And see if you get a better accuracy, if you get a cooler accuracy, I don't know. You can play around with it. We're going to add 2 more layers. Net.add, we're going to do one more dense, which is going to be our single hidden layer in the shallow neural network. You can add more if you feel like it's going to do you better. We're going to do like 14, random number. And then last one, net.add, dense for how many outputs. That's going to be our 2. And there we go. And then lastly, so we're going to have a compile layer. So Keras does this a little bit differently than you would theoretically. So you have a compile layer, which is going to handle your optimization and your activation. So we're just going to use a default optimizer so we don't have to deal with like ReLU and softmax. We're going to do optimizer equals, we're going to do default one, which is RMS prop, which should do us decently well. And then loss, we're going to categorize because there's 2. We're not doing a binary. We're going to do categorical cross entropy, which is going to be able to measure our loss pretty accurately. And then the one metric we do want is accuracy. So there's our compile layer, and that's it. These lines of code right here, these 5, technically 4 lines of code, is the whole neural network. That's what's pretty awesome about Keras. So if fit the configuration, now we're going to train it. So third step is train. It's pretty easy. Net.fit, we're going to pass in our inputs, give it our outputs, and then the number of epochs we want to do. There's other things you can pass into, but these are the simplest. How many epochs? That's the only line to train it. It handles the rest of it for us. Then from there, before we finish the training section, we probably want to get the accuracy. So we're going to do y-scores equals net.predict. So we're going to pass the data through. Keras handles all of it. Test x. Y-scores equals np.argmax, because we want to get the value, or the highest one, set that equal to our value, which one won. Argmax x for x in y scores. And then our accuracy, pretty simple. We're using that function, so we just don't have to write it all ourselves. So accuracy score, which is the one we imported from tflearn, I think, or sklearn, is y true, y score. So we're going to compare what should have happened between what actually happened. And then lastly, we want to know our accuracy, so we're going to do print network accuracy. When it's done being slow. There you go, dot format. And we're going to pass in the value accuracy. Cool. And then from there, that's all of the training you need to do with Keras. It's really simple to get started. So from here, we're going to inference, because it's not fun to do anything if you can't inference it and see whether you have cancer or not. So if you plan on finding out today, good luck. So from there, we're going to inference. And this is where the while true loop comes in. So please don't yell at me or tell my mom. We're going to use a while true, just so we can do it over and over. We're going to do inference string. And Some of you who are Python 3 users, you're going to cringe, but I'm going to do raw input. And we're going to pass in our tensor. Then we got since it's going to come in as a string, we're going to convert it into a tensor. So inference tensor, yeah, spelled right, equals inference string dot split, and we're going to split it on the commas. And then inference tensor. Again, a lot of this could be smushed together, but I wanted to go line by line so people can keep up. Then we're going to do NP array, and then we're going to do some functional, a little bit of functional. Turn each thing into an integer without looping through it, inference tensor. And then lastly, inference tensor, again, one last thing, equals inference tensor dot reshape it, so we have to shape it to what our predictions are going to come out as. So reshape, I'm sorry, what it's going to go in as, to how many inputs. And then the very last line of code, which is the one thing, oh, no, I lied. Results first, equals net, so we got to get our results. Predict, inference tensor, we're going to pass it in. And then now the very last line, which is the fun line, you find out whether you have cancer. So print results. Also, sorry, I'm not trying to make light of this. If this is a touchy subject, I don't mean to be insensitive about medical issues. But I want to bring light to a very real-world application. So it's all done. Hopefully I compile it, and not compile it, I run it, and it's not going to do anything bad. So I saved it. Going to come over here to my terminal. Can everybody see that fine? I think so. Python, that's not how you spell it, Python bc.py. So what this is going to do, we set it up to pre-process. That should be super quick. It's going to set up the neural network architecture, which is going to be super quick. It's going to train, which might take a few seconds, depending if you're using like a Chromebook. It might take like 30 seconds because it's a tiny data set. And finally, we're going to inference on it. So hopefully there's no errors. Cross your fingers. And there's an error. What do we got? Line 35, call new row, call main. Is yours not string? What I'm going to go ahead and do is just do the cheating way, because I don't want to sit up here and debug forever. So where's that at? I'm just going to copy paste this whole thing. You might want to do that too if you followed me verbatim. Was that this line? Yeah. Probably a tabbing thing, I would guess. Yeah, you got a lot of my extra comments in there too now. Okay, so let's see about this. Oh gosh. Oh. Sure. Here, let me just look through it. I don't want to spend forever debugging, like I said. Worst case scenario, I can copy paste the whole source code, I guess. So line 35. Yeah, right here. Converting each row equals whole symbol. So I think we're out of scope. So we want call rows and number. Yeah, so this should be a different value. If I'm totally off, somebody yell at me because I'm not thinking straight when I'm up here on stage. So let's see if this will give it a shot. Saved, right? It did. Yeah, it did. Same thing. Nope, different thing. Yeah. Yep. Well, so we're doing dot values, which I believe should be the header. Not the header, but like the name of the column. Well, no, wait. No, that's the values. So we want... How much time do we have left? I might just copy paste it. 25 minutes? Okay, yeah. Oh, yeah, that's true. Yeah. There should be a separate branch on the repos for Python 3. I had somebody push it. You can take a look. Worst case scenario, look at my past commit. Actually, I have it. I deleted that. Sweet. So I'm just going to copy paste this, I suppose. Yeah, if you find an answer, props to you. Let's give this a shot. And what the heck? Okay, These must be integers, not strings. Let's go back. Sure. Here. Let's go back to my last commit, because I had it working this morning. I had a feeling this would happen. It always happens when you're doing code demos. I converted to make it a little simpler. Let's see. Yeah, so this code, we don't want that. We want the full thing. Let's give this a shot. Okay, I'm assuming it's simple. We'll just go ahead and debug it. Take it back to the original version. And, wow, that went quick. Okay, line 44, new row, or new column row equals column main. And that is a string, not an integer. Line 44. Zach, you wanna hop up here and help out? 44. Okay, let's try this again. Yeah, it had something to do with indentation when we switched to that. Okay, line 35. Okay. New row. So this. Do what? Yeah. Do what? Say that again. I didn't hear you. Yeah, it's lagging. Sweet. Wrong one. Oops. I swear I used Python. Okay, do what? I'm sorry. Oh, in. Makes sense. No, open. Oh, okay. Gotcha. Yeah, okay. I made it worse. Labels class knock XX. Here where's call come from? Yeah. Call's coming from the for loop up here. Yeah, let's just go ahead and open up this file. I got the old version right here. No, but I do have this. This is the one that I used yesterday. Let's give this a shot. If this works, I'll push it to GitHub and everybody can use it. Please work. Yes, there we go. Sweet. Okay. Yeah. Thanks, everybody, for bearing with me there. Okay, so I'm going to push this to GitHub right at the end of this if you want to use the code. Basically what happened, we're going to look through this. It started up using TensorFlow. Keras was the high-level wrapper. Used TensorFlow. We have all of our epics here. It trained ridiculously quick. Went through 10 epics because it's only 700 lines. Went really quick. Got a network accuracy of 94%, which is pretty decent. If you did this over, you might get like 20%. Just because it's a very small data set, very statistically improbable you'll get a good accuracy. So from here, we're going to put a tensor in. I'm just going to do random numbers. 2, 3, 4, 5, 6, 7, 8, 9. So this is going to be our new data. So you just got test results. You're going to put it into the AI to confirm what the doctor said. And here's your result. It's not going through a softmax softmax activation function. So you're going to get the left side is very negative. The right side is very positive, which means that there's a very high chance that you have breast cancer. Very sorry. We'll go ahead and pass it one of the existing numbers and see if we get what it says. So 5, 1, 1, 1, 2, 1, 3, 1, 5, 1, 1, 1, 2, 1, 3, 1, 4, 5, 7, 8. I'm missing 1. 1. Cool. So that gave us benign. And we're going to look at our data set. and the first one is benign. So there we go. Again, I'm going to push this. I'm sorry that the code didn't end up working out with that. If it's on Python 3, it should be super easy. It's just a few changes you need to make. I'm going to push this to the repo, so if you want to take a look at it and do it yourself, you'll be good to go. The data set's there. It'll train it. If it doesn't train, just cancel it, start it again, test it out, see if you have cancer. Good luck. That's it. Does anybody have any questions for me with this very high-level topic? And specifically not questions about what went wrong with the code. Yeah. Yeah. I can just repeat the question if that works. Mm-hmm. Yeah, no, that's a perfect question. So Keras, yes. Keras can use either TensorFlow or Theano. If you have both installed, you have to specify which one. Putting TensorFlow in it is something I wouldn't like to do. The issue comes if you're doing this, if you have a script like this, it's going to be retraining over and over and over. The existing TensorFlow graph tends to stay in memory, and it's one of the issues that's up on GitHub that TensorFlow hasn't figured out yet. So what their recommendation is just import TensorFlow, reset the graph, and start over. So that's all I'm doing in this code up here is just importing TensorFlow, resetting the graph, importing a different part of TensorFlow, resetting the graph, and then creating a new session so it can be blanked. Otherwise, the existing, so if you run it, you get like 2% accuracy, then you try and run it again, it's going to start with that existing accuracy, which you don't want for this situation. So really great question. Observe it. Also, anybody want to yell at me for the while true loop? Cool. Oh yeah, right there. That's a great question. You talking about like the number of nodes in a dense layer? Sure. There is and there is not. There's a lot of theory pertaining to, obviously, your input layer needs to be the number of inputs. Your output layer needs to be the number of outputs you're trying to classify. Between there, it's you can either brute force it, try a bunch of different configurations, see what works, what doesn't. There's some theoretical models that have been proposed in scientific journals as to how to set up the configuration. Some use a little bit of calculus as to each column, how does the value change, like how is the value set up, just plotting that one column. And then based on that, how many layers you should have. The more data you have, typically the denser it should be to compensate for that, be able to find different patterns in different ways. I would say there's no blanket. Somebody can correct me if I'm wrong. There is no blanket rule. It's not like if you have, like we have 9 going in, we have 2 coming out. The 14 I put in is just a random guess. We could put in 2 and probably get an okay accuracy as well, which I passed it. But that's a great question. That's something that a lot of people wonder. This is an old one I use. I'm going to change that to 14. But with that 69 node layer, dense layer in the center, I got a very similar accuracy. So with that being said, it really doesn't matter a whole lot other than just trying it out and see what you get. Cool. Yes? Yeah, so just talking about activation functions. So what's important about activation functions is converting your data into something that is readable. So typically for a multi-class classifier like this, we have, actually typically for this, we have 2 options, benign and malignant. 9 times out of 10, you'd be better off using a binary classifier, which is going to go to 1 node. You're going to use that to determine what it is. And you typically use tan-h. He's the data science guy. That you'd use a tan-h activation function, I believe, for binary classifier, which is going to give you either -1 or 1. You determine based off of that what the answer is. For the sake of this presentation, a multi-class classifier is a little easier to conceptualize, so we use that. We're using a default, we're using the RMS prop optimizer, which Keras has. I think they're using, I'm not sure what activation function they're using. It might be ReLU. But so typically for this, if you want to get a little more in depth, you would have each layer, each hidden layer using ReLU activation, which is going to be 0 pass through unless it's over x, and that's going to be to the rate of x past that. And then if that doesn't make sense, that's okay. And then in your final layer, because you want to determine the probability of each one, rather than getting an answer like this, which is kind of basically gibberish, you would use a softmax activation function, which would give you it would convert these so they add up to 1. So you might get like 32 or 0.32 here and like 0.68 or 0.68 here, which is going to give you more of a probability, not necessarily confidence, but more of an idea of the neural network thinks it's probably about this much that. Again, for the sake of time, for the sake of simplicity, I elected to not handle the optimizer and activation functions. But very great question, because that does apply if you're doing anything in the real world. And yeah.
What's your experience working with recurrent neural network and LSTM in TensorFlow? Is that a good package to use for recurrent neural network?
Yeah. So the question, correct me if I'm wrong, the question I believe is using recurrent neural networks in TensorFlow specifically. You mean like as opposed to Keras or as opposed to other neural network configurations? Okay, so each configuration has its uses. So a deep neural network is great for this. You have data coming in, you're putting data out. And by data, I mean numbers. A recurrent neural network is really great. You're going to convert stuff into numbers first, but it's really great for the recurrent part of it is it remembers what the last one was. So as you are sending data through, it's not only considering all of the data it's been trained on, but what the last 1 or 2 specific things it was, or its inferencing was. So that way, because of that, it's good for like handwriting, for reading handwriting, for natural language processing. It's good because it'll not only remember the entirety of the sentence, but it'll remember what the last couple words or couple letters were, or even just a couple pixels of if you're doing a pen feed. Then kind of a subsection of recurrent neural networks, or RNNs, is LSTM, long-term, short-term, LSTM, long short-term memory, got it. And that's kind of another abstraction of the recurrent neural network. So that way you can get a little bit better accuracy for that natural language processing. And with that being said, other configurations, there's plenty of configurations. There's also convolutional neural networks, which is great for images. You can go even like old-timey, I think it's like the Boltzmann machine or something, which is like a really not useful version of a neural network. If you Google search neural network configurations, there's a bunch of them. It's pretty neat. But each one has their particular uses. But great question.